we worked with on this project who were looking at trying to see how you can classify building data with carbon information. So they have a cloud service, a platform of a service that works with IFC. Nick, I'm pretty sure it's pure IFC that they work with as well. So with that platform, you can build your own software on it to load BIM data, exchange it, communicate with it, and so on and so forth. So they approached us with this challenge, and we said, oh, this sounds like a really good research challenge, let's do a project around it. So I must sort of stress that this is Abdul's project, so if you ask questions I can't answer, I might have to get back to you after the session with answers. And I think, you know, the really exciting time for me as a computer scientist is that we're at this sort of unprecedented time where we have data and technology and resources that we haven't had before, not just in the design phase or the operational phase, but across the supply chain, which makes it incredibly exciting for people like me to come into the domain and play about with data and technology and see what we can come up with. So probably most of us are aware that building data contains lots of information about building products such as material, manufacturer, warranty, and so on and so forth. Great. We also were looking at carbon databases. We only worked with this ICE carbon database, which is the Inventory of Carbon Energy database. There are lots of other wonderful carbon databases out there, but this was a very small master's research project, so we just started off with the ICE database with this particular study. Not to say there aren't more out there. So the idea is that we take the building data and given all these wonderful standards and processing guidelines for generating that data, it should be fairly easy to map the materials from that building product onto any carbon database and come up with some sort of carbon assessment. But as most of us know, the way that those standards and processes are applied are generally or can be inconsistent, which makes it really, really difficult to automatically connect data from different data sources, computationally, certainly. And I've been doing this for many years now, and you know, 10 years down the line, and we're still having these problems, much to my frustration. But this allows us these opportunities to explore these new wonderful ways of working with that data and seeing what we can do rather than forcing people or tools to correct the data. Is there some inferences we can make out the data to automate that process for us? So that led us to this question: can machine learning automate the carbon classification of materials within a BIM? So we did some work on that. Our project was very much a standard machine learning approach. For anybody that's not familiar with how that works, you basically get your data. Data is rarely in any format that you can work with, certainly in the construction sector. So often there's a big job to look at that data, understand that data, clean that data, which means remove any stuff that you can't work with out of the data, prepare it to get it ready that you can do some machine learning with it. And then the next phase is to get that data and develop a nicely trained model. And then with that trained model, you get some test data and see if you can predict some results out of that test data from the trained model. And when you've done all that and got some kind of relevant kind of good solution, you then start trying to improve that solution to take it forward. So the data that we were working with was data out of the ICE database. So we had around about 10,000 rows of carbon data from the ICE database, which had information about material names, labels, descriptions, and carbon classifications, if you like. And we were really lucky, so XBIM gave us 11,500 rows of BIM data. So this was data of industry BIM models, covering various aspects such as IFC family, IFC type, material types, and so on. So the first stage was to really look at that data, understand that data. And what we found within the BIM data is actually things can belong to an IFC family or an IFC type that can be of different materials. So the IFC family and the IFC type definitely does not determine the material. So we were able to drop those columns from that data and work with a much smaller data set here. Some of the items within the data that we were using were already classified, some of them weren't, so the challenge was to kind of predict what those unclassified things were, or see if it was possible to predict what those unclassified things were. So within our overall data set, our data was very unevenly distributed, which meant that it could have led to sort of biased predictions, and we didn't want that. We wanted to avoid that. So we used this sort of technique called synthetic minority oversampling technique, or SMOTE for short. And all that does is create a more sort of evenly distributed data set there, so that we're not working with uneven data. So the next stage, stage 3, is the model training stage. So we chose to use these 3 algorithms. These are 3 sort of commonly known classification algorithms. There are other algorithms we could have explored, but you've got to start somewhere. So the first one we were looking at was a recurrent neural network with long short-term memory. And for those that aren't familiar with those kind of algorithms, it's essentially a set of layers. The architecture is a set of layers. And in each layer, you've got nodes and neurons, and you pass the data through each layer. And as the data goes through each layer, the algorithm makes some assumptions, then it goes to the next layer, makes some assumptions based on the memory from the previous layer, and so on and so forth, until it gets to the end of its journey and says, this is my prediction. With random forest, that works slightly differently. So you put some data into the random forest algorithm, it splits that data off into branches, each branch does some random sampling, it makes some decisions about what it thinks that data is, and at the end of the branches it has a sort of voting mechanism to say, right, out of all the decisions I've made in this tree, these ones are the most common that have come across, so we're going to vote for this classification. And the last one is naive Bayes, which is a fairly simple probabilistic algorithm that basically says, based on your features, I think you are this thing over here. So those were the 3 algorithms that we chose to evaluate our data with. We thought that gave a fairly comprehensive range of the different approaches from a starting point for this type of journey, excuse me. But as I said, there are a lot more approaches we could have tested, we just didn't have time or resource for this particular project. So typically within a machine learning model training scenario, you take your data and you split it. So we had 80% of the data was trained. So the trained model is saying, this is what these product items are classified as. And the 20% was our test data. So you run through your test data and say, can you predict what these things are on this 20% test set against the training model? And I did talk earlier about sort of improving the model. So there was some work around hyperparameter training and optimization just to kind of improve the way that the models were applied and worked as well, to get better results, basically. So these were the results that we got. So as you can see, we've got the 3 sort of algorithms down the left-hand side there. And these are the sort of precision recall and F1 score results, each one sort of testing the model slightly differently to see how successful it was. So at the top, we've got random forest scores very highly at 99%. That's a really good score. Naive Bayes comes second, and RNN performs the poorest out of the 3 algorithms. So as well as the sort of prediction of sort of whether we think this particular item is a piece of steel or a piece of wood or whatever it is, there's another thing that we can do, which is test the confidence level of each of the algorithms. And the confidence level says, okay, well, you predicted that item to be that thing, but how confident am I that you are actually right in what you predicted there? So when we tested the confidence level, we found that naive Bayes performed really poorly. So you can say 18% a low score, 3% a really low score. So we weren't confident at all that those naive Bayes predictions were accurate at all, really. But with random forest, you can see that these confidence levels are much higher here. So I think this gives a good indication that we could possibly continue some research around the random forest algorithm for predicting materials within the BIM data and connecting it to the carbon data. So back to our original research question, can machine learning automate carbon classifications of materials within a BIM? Well, I'm not here to make any grand assumptions or declarations. This was just a starting project. It certainly gave us the foundation for seeing whether machine learning could make some predictions, but before we'd be confident about putting this forward as an end solution, as it were, I think there's a lot more work to be done. So, you know, we need bigger data sets to make it more generalizable. We could really do with some of that test data, training data being more classified more, so to give us a better trained model. So there's certainly a lot of work to do to kind of validate and verify these results. So thank you, that's me done. Thank you for listening and for coming along today. Thanks to XBIM for providing us with access to the data. That's what was really, really useful, because it's always hard to get your hands on data. Thanks to Abdul for writing the paper and allowing me to come to this beautiful island and meet everybody and swim in the beautiful ocean. And that's it. Thank you.